In today's video, we'll be looking at the 2004 Physics C Electricity Magnetism Question 1 from the free response question. So what they give us at the beginning of the question is a figure above shows a hollow, infinite, cylindrical, uncharged conducting shell of inner radius R1 and outer radius R2. And there is an infinite line of charge density plus lambda is parallel to the axis, but it is off-centered. Part A asks us, on the cross-section which will be shown, to sketch the electric field lines, if any, in each of the regions 1, 2, and 3, and then use plus and minus signs to indicate any charge induced on the conductor. So first, we see the figure here drawn from part A, where we have a charge of plus lambda just off-center within a ring of charge itself. And then we see region 1 is the white area within the red ring, region 2 is the area of the red ring itself, and then region 3 is just outside, with R1 being the radius of the white area inside of the ring, and R2 being the radius to the outside of the ring. We also see points A, B, C, D, and E scattered throughout. So it first asks us to draw the electric field lines from this surface. So what we know is that the electric field lines have to come out at 90 degrees, and they also intersect at 90 degrees. So the easy ones to draw are on the outside shell, where we can just draw straight lines out like the rays of the sun, 360 degrees around the ring. But the electric field lines off of the plus lambda charge are a little bit different. These lines will actually curve, as seen here, so that the electric field lines will actually intersect at 90 degrees with the inside of the ring of the shell of charge. If they did not do this, then the electric field would be incorrect, because the electric field has to intersect at 90 degrees with the actual surface, as that is how electric field passes through surfaces. Part B of this question asks us to draw positives and negative symbols where positive and negative charge would be. So because there is a positive lambda charge inside of the ring itself, and the ring is uncharged, this means there's going to be a distribution of positive and negatives within the ring itself in order to keep it uncharged. So as there is a positive in the center, it's going to actually attract more negative charge towards the inside, making the negative charges, as seen here, going around the inside of the ring, with more negatives being concentrated near the positive charge, as that is where the pull is the strongest. And then that will leave the positive charge around near the outer shell of the ring in order to counterbalance the negatives on the inside. Since the charge of the ring overall is 0, there has to be an equal balance between the positive and negative charges within the ring itself, within the shell. Part B asks us, in the space below, rank the electric potentials at points A, B, C, D, and E from highest to lowest, 1 as being the highest. If 2 points are at the same potential, give them the same number. So we know that the electric potential is strongest near the source of the charge, which in this case is plus lambda. So if we took a look at all of these points, we see that D is the closest to plus lambda, so it would have the largest charge. C would have the second largest charge because within the ring, close to plus lambda, but it's not as close to plus lambda as point D is. Point B and E would have the same electric potential because they are both within the neutrally charged ring itself. And then point A would be the lowest, or ranked 4th, as B and E are both ranked 3rd, but point A would be the lowest because it is the furthest away from plus lambda, and it is also located outside of the ring of the neutrally charged shell of the ring. D would have the highest electric potential, while A has the least, and B and E would be the same, while C has a higher potential than B and E, but less potential than D because it is further away from the charge itself. This brings us to part C. It tells us the shell is replaced by another cylindrical shell that has the same dimensions but is non-conducting and carries a uniform charge density of positive rho. The charge is positive rho because the charge is spread out throughout the entire ring instead of just on the surface like a conductor. The infinite line charge, still of density positive lambda, is located at the center of the shell, unlike off-centered. Using Gauss's law, we need to calculate the magnitude of the electrical field as a function of distance r from the center of the shell for each of the following regions, where r is less than r1, where r is greater than r1 but less than r2, and where r is greater than r2. So first, when r is less than r1. So we know that Gauss's law is the integral of E dot dA equals the Q enclosed over E naught, which is a constant. So we were told from the problem that the charge of the line was positive lambda. So we know that to find the Q, we need to use the equation lambda L, which is the charge density of a line of charge. So we'll plug that in for Q. We also were told that it was a line of charge, and we know that the best shape to surround a line of charge is a cylinder so that we can only have to deal with the area of the fat part of the cylinder and not the edges, but just the middle, where it turns into a rectangle. So the area will be 2 pi RL, which is to find the surface area of the rectangle of the cylinder. So if we plug that in, we'll get the electric field of the line times 2 pi RL, which is the area, equals lambda L over E naught. And then we'll find that the electric field is lambda over 2 pi R naught, because the L's cancel out. Secondly, we're going to find when R is greater than R1 but less than R2. So we know that we can add up the total electric fields to find the electric field itself inside an enclosed area. So in this case, we'll be adding up the electric field of the line plus the electric field of ES, EL plus ES, and that will equal E total. So we've already figured out EL, so now we just need to figure out ES. So we were told that the charge of the ring itself is positive rho. So to take the Q of this positive rho, we need to take the rho and multiply it by 2 pi r squared L minus 2 pi r1 squared L. This will give us the enclosed volume of the ring of charge when r is between r1 and r2, because it can be a variable, so we have to show the variable. And we use 2 pi r squared L because that is the volume of a cylinder, which we would use in this case because a cylinder would fit inside a cylinder, which is logical to use. So just as before, we have EA equals Q over E naught, just the standard form of Gauss's law. And then if we plugged it in, we'll have ES times 2 pi RL equals rho 2 pi r squared L minus 2 pi r1 squared L divided by E naught. And then if we move the 2 pi RL over, we'll discover that the E shell equals rho times r squared minus r1 squared, because the pi's and the l's cancel out, divided by 2r E naught. So the E total of when r is greater than r1 but less than 2 would be the E of line, which is lambda divided by 2 pi r E naught plus rho times r squared minus r1 squared divided by 2r E naught. So this brings us to where r is greater than r2. So we're going to use a similar strategy from before, but just with a couple of different numbers. So we're going to use the same strategy of the electric field total equals the electric field of the line plus the electric field of the shell. So we still use the same electric field of the line because that hasn't changed. It's a constant thing the entire time. But the electric field of the shell will change this time. So this time the QS, or the charge of the shell, is equal to rho times 2 pi r2 squared L minus 2 pi r1 squared L. We use this because this is the total volume of the ring, and because r is greater than r2, the Gaussian cylinder that we're going to put around this thing will enclose the entire charge of rho and its entire volume. So that's why we use r2 squared minus r1 squared, because that is the total volume of that ring. So similar as before, we're going to use Gauss's law to solve for E shell. So EA equals Q enclosed over E naught, just Gauss's law. And then we plug in 2 pi RL, again for cylinders. And then we plug in the Q of rho times 2 pi R2 squared L minus 2 pi R1 squared L divided by E naught. And then we just divide the area and we get E shell equals rho times R2 squared minus R1 squared and divided by 2R E naught, where the pi's and the L's cancel out. And then we're left with the E total, where the EL is the same as before, lambda over 2 pi R E naught, plus rho times R2 squared minus R1 squared divided by 2R E naught. And that is the E total when R is greater than R2.